Okay, so the deal with 57 is so we'll start by saying that this problem has some issues, okay? So I'm going to, but everything that I talk about and cover is all good reasoning and worthwhile to think about and do. But if you struggled, it may partially be because it kind of needs to be reworded, okay? So here's the way we want to think about this. T is the time since started driving, or the time since leaving Denver, in hours, right? And the distance is D equals distance from Denver in miles. So they give us a couple ordered pairs here. They give us 1/2 hour, 1:55, and 2 hours, 2:60. And they say that she's traveling at a constant rate. So we have to, because of what's going on here, we have to assume that the constant rate is really starting at 1/2 hour. Okay? So it's starting at 1/2 hour, and 155 miles from Denver is when she puts the cruise control on. Okay?
Oh, I thought it was when she left.
Right. It can't. So if it's starting from when she left, then it can't be a constant rate of change.
Oh, that's why I thought we were finding
right.
If it was a constant.
Well, it is a. So what the intention was, the constant rate of change is starting at 1/2 hour. Okay.
Okay.
I know. And let me just say, so don't just copy all this down in your homework and without thinking. So the idea of going over this is that it's helping you to make connections, helping you to understand it better. So don't just mindlessly write and copy so that you can turn it in Friday, okay? So really try to engage as we review some of these ideas from both Module 2 and Module 3. Okay. So how would we calculate this constant rate of change if at 1/2 hour it's 1:55 and at 2 hours 2:60? Yeah, so our constant rate of change or constant speed is going to be the change in distance over the change in time. So we're going to take the change in distance. So remember, our change is always found by subtracting final minus initial. Final distance minus the initial distance, that will be how much the distance increased, right? How much it increased would be your final distance minus your initial. Same with time. Final time minus initial time would be how much it increased or how much it changed. When you do all that math, you get 70 miles per hour. So we're just going to assume starting at 1/2 hour is when the cruise control is on, 70 miles per hour, constant rate of change. So they want us to come up with the function f. What's the input into f? Is it t or d? Input's time, output is distance. And so if we want a rule for this function, is the rule going to have t's in it or d's in it? It's going to have t's, right? The rule is always acting on the input to give us the output. So we need some rule with t's. Okay, so I'm going to go over, so to build this rule, and we know it's constant rate of change, I'm going to review again what we did that one Friday. So one more time. This may be unfamiliar and not the way you would approach it, but this way really engages your understanding of quantities and how they change together. So we have the starting point. We could pick either point. We could pick 1/2 55 or 2 260. I'll just pick 2 260. We have the starting point, and you had homework like this. And we're really asking, at any other time t, what's the corresponding distance? That's coming up with the rule. So given some other time t, we want to know what is d. And that by finding out what d is given this t, we're creating that rule. That's what we're doing. So what was the first step in that process? Anybody remember?
The change from 2 to t.
Good. Yeah. The first thing we looked at was how much does our independent variable change? And what is the change from 2 to t? 2 plus t. Agree with that? How much do we change if we start at 2 and we end at t? How much did t change between those two? Yeah, it's going to be final time minus initial time. That's how much t changed. Because these are both referenced from 0, right? This is 2 from 0. This is t from 0. So to get that change is going to be this minus that, or t minus 2. All right, what was the next? So good. So what was the next thing we did? So one person remembered. Awesome. Corresponding change in distance. And how can we do that? The corresponding change in distance is based on constant rate of change. All changes in distance are 70 times whatever change in time you have. If you go 2 hours, you go 70 times 2 in distance. If you go a half an hour, you go 70 times a half. So our time is t minus 2 that we've gone. So our change in distance is always going to be 70 times that change in time. This is proportional reasoning. So
the problem doesn't really make sense though, because you go like 300 miles an hour, wouldn't you?
So the constant rate of change is starting with at half an hour. Right, I said there was issues with the problem. Did you come in late? Okay. All right. I said there was issues with the problem. We're starting at a half an hour. That's when the cruise control starts. Okay, so what is this change in distance? So at 70 miles per hour, changes in distance are always 70 times is our constant multiple proportional reasoning. No matter what time change you have, your change in distance will always be 70 times that. That's proportionality of the changes. All right, so what is delta D? 70 times our change in time, t minus 2. All right, so we started at 260, and we want to know what we ended up at. So d is going to be this initial distance we went, but then we have this change in distance. So how do we factor that in? No, we just add it, right? Initial, where we were, plus the change is going to be our final distance. So where we were, 260, plus the change in distance is going to be our final distance. And so that is the rule that gives us d in terms of t, and so we can, that's our function rule. So f of t equals 260 plus 70 over t minus 2, or times t minus 2.
For this problem, we're going to start at 155 with the problem.
What's that?
For the answer.
Yeah, so let's plug. So if you plug 1/2 in for time, we ought to get 155. And if it does, then it works. So if you plug 1/2 in and work this out, you will get 155, and it works. See, this is any point. So we could have started at 260, or I could have started at 1/2 at 155, and it should work. Yeah?
You start at 260 because your change in distance starts at 260? Like 260 plus 70?
Yeah, so the reason I started at 260 is because we started at 2, and those are a corresponding pair.
Okay.
So at 2 hours, you're 260 miles. So if I'm going to start at 2, then I have to also start at 260. So that's a corresponding pair. So we could have started at 1/2, and then this would be 155. And you get the same exact rule. Okay, so any questions on that? So remember, we spent a whole Friday working on that, and then you had homework problems and that kind of stuff. So that's like Module 2 review stuff. Can I erase the screen? Okay, so then it's asking about the inverse. So we have that f of t is final distance plus the change in distance. T minus 2 times 70. Thank you. Okay, 70. Good. So what then F inverse, what is the input and what is the output? So the reverse process of this process, which takes time and gives distance, F inverse will take distance and give time. So F inverse, what does the 500 mean if we're taking F inverse of 500? So the distance is 500, and this function will give time to reach 500 miles.
What is that time from 260, time from 155, or time from Denver?
It's the original t. So our t was time since we started driving, and distance was distance from Denver.
Okay.
So it's the same quantities, just flipped.
Okay.
Yeah, it'll be the same quantities as the original function, but now they're just swapped. Okay, so time to reach 500 miles from Denver, because that's what d was. So to calculate that, we're just we can use this, right? And where's the 500 going to go? So the input into F inverse is the same as the output, or distance, so we can say 500 equals 260 plus our t minus 2 times 70. Solve for t. And that would be finding the output. So finding this input of F would be finding the output of F inverse. Does that make sense? Okay, finding a rule for F inverse. We said F inverse will be D, or of D. So will the rule have D's in it or T's in it? Have D's. So we need T equals some formula of D's. So we can get that from our relationship that we found. And we need a rule that has T equals something with D's. So how can we use this to find that rule? T equals some formula of D's in it. What do we do? Yeah, so we're going to get T by itself. We're going to isolate T, and once we isolate T, we'll have the rule. We'll have a formula. So the first step is subtract 260. Then
Multiply the 170 into.
we're going to divide by 170. And then third step, add 2. So we'll start with a D. First step was subtract 260. Second step, divide by 170. Third step, add 2. 70. Sorry, just 70. Just 70. So that's the rule. Now that's the inverse rule. That undoes what this one does. It takes D and gives T. We're not going to do the graph. Any questions on this? So there's lots going on here. Constant rate of change and inverses. Last chance before we go on. What does it mean that F and G are inverses of each other? Yeah, so the F function we know that if you put 2 into F, what do you get? 23. Now, If G is the inverse of F, what does this tell us about F? This statement right here, what can we deduce about F if G of 12 is 1.7? What's that? Yeah, so if you put 1.7 into F, what would you get? You would get 12 out. Okay, similarly, G is the inverse, so if G is the inverse, then what, we know for sure that G of 12 is 1.7. Do we know anything else? We know what would happen if you put 23 into G. You would get 2. So based on the information of the problem, so we know f of 2 is 23, but then based on this, we also know that f of 1.7 is 12. And then we know that G of 12 is 1.7, but because G is the inverse of f, then the input, if the input of G was 23, its output would be 2. Okay, so what's G of 23? 2. What's f of 23? We don't know. We know what f of 2 is, and we know what f of 1.7 is, but we don't know what happens if you input 23 into f. Unknown. Okay? F of G of 23. Well, G of 23 is 2. And so what's f of 2? 23. Okay, so here's a new one. G of f of 3. Can we determine it? So here's the question. Can we determine f of 3? No. I'm going to write it here. We don't know what it is. But we're going to take that, whatever it is, and we're going to put it into G. Do we know what that will be?
3.
It'll be 3. Why? Because G is going to undo whatever F did. So we don't need to know that middleman, because if you put 3 into F, it'll give you something. But if you put it through the reverse process, G, it'll give you back what you started with. So even though we don't know what F of 3 is, we still know that G of f of 3 is 3.
Could you say in simple terms that, like, if F puts in its information into G, it's always going to get its own information back, just the opposite, and you can do it the same through G? Because that's what it looks like. If I put in...
Just keep telling yourself, as you practice it, keep telling yourself, G is the reverse process. It undoes what F does. So if F, you put an input into F and it gives you an output. If you take that output and put it into G, give you back what you started with. Keep practicing that, and then in terms of doing these.
Could you say that G of x equals x?
Does it equal X? Yeah, because whatever you put into F and get an output, G will undo that process and give you back what you started with. And we showed that with the temperature functions on Monday. That's exactly what we did with the temperatures functions. Same with f of g of x. You put some value into g, it'll give you an output. If you put that output through the reverse process, or you undo it, you're going to be back with what you started with. Does it help? Okay, so that's a nice lead-in to these practice problems. So now work on these. dependence, which we put into G, and that gives you the Does it work?
Yeah. It's not, it probably will be 0, but.
Does not work. Why? What is the output of G? What is the output of G? Revenue. What is the function of F? To take what? To take temperature. You're trying to put revenue into a function that wants temperature. Doesn't work.
Just the number. I thought we put 10,000 in for.
No, it's all about the meanings of the quantities. Is it a valid process? No, because G gives revenue out. So you're trying to put revenue into F. F takes temperature and gives number of people. It doesn't know what to do with revenue. The 100 is number of people going into G. But what's the output of G? That produces revenue, which is now in the composition, the output of G is the input of F. So you're trying to put revenue, the output of G, as input of F, but the input of F is temperature. Make sense? Doesn't work. What about this one? Does it work? What does the 100 represent then? Yeah, so this is the output of G. 100 is the output of G. And so X then is the temperature leading to a certain number of people that we put into the G function and gives us this amount of revenue. So it's the temperature leading to that amount of revenue. Okay. What does this mean? What is the 70? If it's the Yep. This is now, if it's the input into F inverse, it must be the quantity that's the output of F, which is number of people. So then the output of F inverse would be the input of F or the temperature. The temperature corresponding to an expected 70 people at the concert. Does it make sense? Mm-hmm. Okay, I'll take requests now. I don't have time to do them all. So F. So F is tricky. You've got lots of inverses going on here. So let's talk about the G inverse function. What is the input into G inverse? The input into G inverse would be the output of G, revenue. What's the output of G inverse? Number of people, because it'd be the input into G. Is the input into F inverse number of people? In other words, is the output of F number of people? Yes. So this is the inverse now. So the input into the inverse would be the output of F, and the output of F is number of people. So it works. Then your answer, it would be the output of F inverse would be the input of F, which would be temperature. It works. So this whole thing is the temperature related to what? A revenue of 80, 100, 8,000, yeah. So this works. F is good. Did you catch it? Does it make sense? This is important that you can really track those quantities. Last one, G. What would 90, looking at this, what kind of quantity would 90 be? Output of F inverse, right? Output of F inverse or input of F. So 90 would be temperature. So let's see if it works. What's the output of g of x? Revenue. Is revenue the input of f inverse? Or, in other words, is it the output of f? Doesn't work. Because you're trying to put revenue into the f inverse function, which would mean that revenue would need to be the output of f. And it's not. So this doesn't work. Not valid. Okay, so if you didn't write them down, then just find it on the video and just pause it on the video and you can work more on it, okay? So I want to talk about the difference quotient. That was your last question. Okay, remember the open top box? The volume of the open top box. This was the volume function. And so what this difference quotient is about is, it's about starting at some value x. So let's remind you. So x was the side length of the square cutout. Okay, and f of x was the volume of the resulting box. After we cut out the squares, folded up the sides, right? So this would be like, could be inches and cubic inches. No, I'm just talking about this concept of the average rate of change. So what average rate of change is, it's about looking at some change. So we can start here at x. Okay? And now I'm gonna increase the side length cutout by h. So from here to here is h. So what is the final value there of x? If I start at x and I increase x, if I increase a change of, if I do a change of x of h, what's my final value of x? X plus h. Okay, so the input, so it's about a process where input starts at x and goes to x plus h, which means a change of h, right? And we're going to track, simultaneously we're going to track, so meaning we can start at any input value and take any change that we want. We start at any x and we have any change h. So I'm just showing it there at a specific place. So when we start at x, what is the value of the function, or in this case volume? What is the output going to go from what to what? So when we start at x, what does the output start at?
Sorry, do you know Laura Gonzalez anymore?
Laura?
Yeah.
Laura Gonzalez?
She's on this floor, supposed to be in the Native American.
She's not. Well, there's offices for that all around here. This is a math class.
Oh, sorry about that.
Okay. I thought it was an emergency. It was a sub-delivery. Okay. So, all right. So x. So what, as the input goes from x to x plus h, what's the starting value of the output? How do we represent that starting value of the output then? F of x. So this is f of x. And then what's the final value of the output going to be?
F of x plus h.
So as I increase from x to x plus h, the final value of the output, f of x plus h. So the question is, as we changed the input by h from x to x plus h, how much did the output change? How much did the output change? How could you express how much did the output change?
F of x plus h minus f of x.
He wants f of x plus h minus f of x. Do you agree? That's the key. So the change is going to be the final output minus the initial output.
Change of what?
Change of output. Right? It's this change right here. From the starting output to the final output. Changes this much. Okay, so the constant rate of change, the average rate of change. Remember what we said average was? Average rate of change or average speed? First and foremost, it is remember what average speed was?
Rate of change needed to travel a specific distance in a specific manner.
Right, so it was a constant, right? So it was what was the constant rate of change or the constant speed to get the same distance in the same time? It's the same thing here. It's the exact same principle. Average rate of change is the constant rate of change to get the same change in output for the same change in input. It's the exact same principle as average speed, but now it doesn't have to be distance and time anymore. Like for us, it's the square cutout and it's the volume. But it's the exact same principle. It's the constant rate to get the same change in output, which we've said here, for the same change in input. So on this graph, what would that look like? So we started here, and we're finishing up here. What would the constant rate look like to get the same change in output for the same change in input? So here's our change in input. Here's our change in output. What would the constant rate look like to get that same change in output for the same change in input?
It's a line between the two.
Yeah, so the constant rate of change would be linear, right? Pretend it's linear. Not too bad. Okay, so it's really thick. Try it one more time. There we go. Okay, so this represents then that constant rate. And so it's going to be change in output. The constant rate of change will be change in output per change in input. Or, well, we already found that. What is the change of output? F of x plus h. The final output minus the initial output over h, or x plus h minus x. So this is the average. This is the difference quotient, which finds the average rate of change. Difference quotient finds the average rate of change. What constant rate would we need to go in order to see that same change in output for that given change in input? So all the meanings of all this is important. So you should review, break it up into pieces and ask yourself, what does that piece mean? What does that piece mean? What does that piece mean? Okay? Really important. Okay, so your exam is tomorrow. If you're, so I'll give you all the instructions Monday. The deadline for the bonus on the web work is tonight at midnight. Yeah, I'm going to collect them Friday.